Okay, let's see how you made out with problem 12. You're asked to find the log of 215 to the base 7 so you can convert to log base 10 using the formula. Log base 10 of 215 over log base 10 of 7. That's what this is equal to. Look up each of those logs on your calculator and you get there, do the division, and you get approximately 2.760. Now, is there any way to check your result here? Well, not in an exact way, but you can get a pretty good feel for if you got the right answer or not. 2.760, okay, that's more than 2, but it's less than 3. Now, 7 raised to the power 2 is 49. 7 raised to the power 3 is 343. We are basically trying to get 7 to such a power that it equals 215. 215 is between 49 and 343. So it seems pretty plausible that 7 to the power 2.760 is going to land where we want it to land, at 215. And in fact, 2.760 is closer to 3 than it is to 2, so you would expect that when you raise 7 to that power, you're going to get a number closer to 343 than you would get to 49, which is what 215 is. So that seems pretty plausible. I think we've got that one done correctly. Next topic, solving solving exponential equations with log properties. Let's look at example 6 on page 349, part B. 6 times the quantity 4 to the power 3x minus 2 equals 120. First thing clearly to do, divide each side by 6. That cleans things up a bit. Now we have the exponential expression by itself. Different bases, this is 4, this is 20, of course it's 20 to the power 1, the invisible 1 is always there as an exponent. So I'll take the log of each side to get this exponent down here. So when I take the log of each side, the 3x minus 2 can be placed right there as multiplying the log of 4. So I've moved my exponent out to there. Let me divide each side by the log of 4. So I arrive at this statement. 3x minus 2 equals the log of 20 over the log of 4. I compute these two logs on my calculator and I get 1.301 over 0.602. Perform that division and I get approximately 2.161. But that's what 3x minus 2 equals. So I'll add 2 to each side and I'll get here 3x approximately equals 4.161. I need a little more space, so I just drew an arrow here. Divide each side by 3 and I get x approximately equals 1.387. And by the way, if you look in your textbook, the text used natural log to do this. I used common log just to show you it doesn't matter which one you pick. Either way, you're going to figure it out. And you're going to figure it out right here. Do number 20 on page 354. Okay, how did you make out with number 20? In this problem, you're given the equation 3 to the power x minus 4 equals 140.3. So what you want to do to get that variable out of the exponent and down into the main expression, take the log of each side. You could have also taken the natural log of each side, doesn't matter. Here I can move my exponent, x minus 4, out there, so I get x minus 4 quantity times log 3 equals log of 140.3. I divide each side by log of 3. So I get x minus 4 equals log of 140.3 divided by log of 3. Do the calculations, I get approximately 4.500. But that's what x minus 4 is. So I add 4 to each side and I get x approximately equal to 8.500. Is that a plausible answer? Well, if I plug 8.5 into there, it's 8.5 minus 4, so that gives me 4.5. Question becomes, does 3 to the power 4.5, does that seem like it would be equal to 140.3? Well, 3 to the power 4 equals 81. 3 to the power 5 equals 243. So yeah, 140.3 falls in the middle there, so it seems pretty believable that this number is going to work for us. And that's how we would do number 20. So, let's go to page 350 in the textbook. And our topic there is solution of log equations. Not exponential equations, log equations. By converting to exponential form. So we see on page 350, example 7. This is a log equation. It's an equation that has a log expression in it. 4 times the log of x to the base 3 equals negative 8. Well, you could do conversion and get away from log of 3, convert it to natural log, or convert it to common log. Or you could just do this, which is simpler. Convert this to an exponential equation. First step, of course, divide each side by 4, and we come up with that statement right there. Now we know what this means. The base 3 raised to the power negative 2 equals x. That is the definition of a log function. In other words, x equals 1 over 3 squared. In other words, x equals 1/9. Let's look at example 8. Six plus 3 times the natural log of x equals 12. Well, of course you want to isolate that x. That's what solving the equation means. In this case, of course, your best strategy is isolate the log expression, just like we did over here. So I'll subtract 6 from each side. That leaves me with 3 times the natural log of x equals 6. Divide each side by 3. So I get there. Now, keep in mind what the natural log of x means is log base e of x, and we could write it that way if we felt like it. Converting this to an exponential equation, just like we did in the previous problem in that approach, this says that the base e raised to the exponent 2 equals x. And there's our answer. E squared. Well, e times e is going to be some number around 7 or 8, I forget. But, e is 2.7 dot 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 dot. So 2.7 times 2.7 is going to give you 7 or 8, something like that. Now, That's pretty good, but these are simple ones. Each one of these examples has only one log expression in it. In real life, you're going to get more complicated equations involving logarithms. Look at example 9. Natural log of x plus 3 equals natural log of the quantity x plus 4. So we've got two log expressions there. How would you approach this? The previous approach of just immediately converting everything to exponential equations is not going to work in this messy situation. What you want to do is get all the logs on one side. In this problem, I'll do that by subtracting natural log of x from each side. So I arrive there. What does that do for me? Well, I don't have it on my properties boards here, but the difference of two logs that are to the same base is equal to the log of the quotient, this number divided by this number. In other words, right? The log of this number divided by this number is equal to the log of the top number in your fraction minus the log of the bottom number in your fraction. So, we know that that equals 3, of course. Now, we can convert to an exponential equation. We've got things straightened out to where we've just got one log expression. Right? So that was our strategy. Get the logs together, use the laws of logarithms to convert this to just an expression of a single log. We know that this means that the base e raised to the power 3 equals the number we're taking the log of. And again, e is a constant, right? This is an actual number here. It's 2.7 something times itself again. So you're going to get something around 20, something like that. And now we just solve in the usual way. I'll multiply each side of the equation by x, and the next good step here would be to subtract x from each side to get x on one side. So I'll get 4 equals x times e cubed minus x. Let's continue up here. All the x's are on the right side. Let me factor out x. I arrive there. 4 equals x times e cubed minus 1. Divide each side by this number here, e cubed minus 1. And there's my answer. If you want a decimal approximation, it turns out it would be equal to approximately 0.21. Do number 34 on page 354. This again involves two logarithms, and you're going to have to combine them together to get it down to one logarithm. Okay, how did you make out with number 34? In problem 34, we have the log base 2 of x equals 3 minus the log base 2 of 2x. Okay, we've got the same base 2 here and here, so we don't have to convert bases. That's nice. But we have two logarithmic expressions. We need to somehow combine them together to get just one. So what we can do is add the log base 2 of 2x to each side. So I arrive at that statement. When you're adding two logs like this, both to the same base, one of our properties applies. It's actually property 6, as I recall. That is the same as that. So I've got it down to a single logarithm. I could rewrite this thing as an exponential equation. This is base 2. Let me put the base in there. This says the base, 2, raised to the exponent 3, equals the number we're taking the log of, which is 2x squared. Finishing up. First thing to do, I've got 3 powers of 2 here. I have a single power of 2 here. Let me just divide each side by 2. So I get 2 squared equals x squared. In other words, x squared equals 4. Take the square root of each side. Algebraically, it gives you, sorry, that's a 2. It gives you two numbers, plus 2, minus 2. But we know you can't take the log of a negative number, so there's no way we could plug x equals minus 2 in there. So my answer must be x equals positive 2 only. Can you check your answer? We always love to check if we can. Let's go to the original equation. And we'll plug in x equals 2. Okay. The log of 2 base 2 is 1. Over here I have 3 minus the log base 2 of 2 squared. I can move my exponent out front and say this. We know that the log of 2 base 2 is just 1, so that factor can just disappear. I get 3 minus 2, which equals 1, and it checks out. For homework, on page 353, (1), (3), (11) through 17 odd, and 25 through 33 odd.